The Moon is closer to Earth than any other world we have ever visited. At its average distance of 384,400 kilometers, the Moon is close enough that light takes only 1.28 seconds to travel between us. Close enough that the Apollo astronauts made the journey in 3 days. Close enough that in an emergency, a real emergency, a rescue mission could, in principle, be launched and arrive within a week. Close enough that radio communications are essentially real-time, with a delay measured in fractions of a second rather than minutes. By every measure of proximity, the Moon is the most accessible destination in the solar system. It is the obvious first step for any human expansion beyond Earth. It is the place we have already been. It is the place most space agencies and most serious proposals for human space exploration identify as the next permanent human outpost. And yet the title of tonight's program makes a claim that seems to contradict this obvious logic. Living on the Moon is more dangerous than living on Mars. This claim is counterintuitive. It seems wrong. Mars is farther. Mars has a thinner atmosphere. Mars has lower gravity. Mars is harder to reach. Mars takes months to travel to rather than days. If something goes wrong on Mars, there is no quick rescue. By every naive metric of danger, distance, difficulty, inaccessibility, Mars should be more dangerous. But naive metrics miss something important. Tonight we are going to follow the specific, physical, verifiable reasons why the Moon presents hazards that Mars, in several crucial respects, does not. Not because Mars is safe, it is not. Not because the Moon is a death trap that cannot be survived, it can be. But because the specific combination of conditions on the Moon produces dangers of a character that are in some ways more difficult to manage than the dangers of Mars. Understanding why requires going deeper than distance. It requires understanding radiation, gravity, dust, geology, and the specific physics of what each of these worlds is and what each does to human biology and human technology over time. If you have this on because the night is long, stay. The comparison between the Moon and Mars reveals something specific and surprising about what makes a world habitable and what makes it hostile. And the answer is not what most people assume. Let us begin with the most fundamental comparison, with what each world actually is. The Moon is Earth's natural satellite. It formed approximately 4.5 billion years ago, almost certainly from debris ejected when a Mars-sized body called Theia collided with the early Earth. The Moon has no atmosphere, no magnetic field, no geological activity in any meaningful sense, no liquid water at the surface. It is, in the most literal sense, a dead world, a ball of rock exposed directly to the full environment of space, with no protection from anything that environment contains. Mars is the fourth planet from the Sun. It formed at approximately the same time as the Moon from the accretion of material in the early solar system. Mars has a thin atmosphere, about 0.6% of Earth's atmospheric pressure, composed mostly of carbon dioxide. Mars has no global magnetic field, though it has localized patches of remnant magnetism in its ancient crust. Mars has geological features suggesting past water, dried river channels, ancient lake beds, polar ice caps of water and carbon dioxide ice. Mars is cold, dry and inhospitable, but it is not as completely exposed to space as the Moon. These differences are crucial. They are where the comparison gets interesting. Let us start with the most immediately life-threatening difference: radiation. On Earth, we are protected from the full radiation environment of space by two overlapping shields. The first is Earth's magnetic field, the magnetosphere, which deflects the charged particles of the solar wind and prevents them from directly reaching the surface. The second is Earth's atmosphere, a column of air roughly 10 kilometers thick at sea level, which absorbs and scatters high-energy radiation, attenuating it to levels compatible with biological life. Remove both of these and you are exposed to the full radiation environment of space. This is the situation on the Moon. The Moon has no magnetic field. it lost whatever magnetic field it once had approximately 3.5 billion years ago. The lunar surface is directly exposed to the solar wind, the continuous stream of charged particles flowing outward from the Sun, and to galactic cosmic rays, extremely high-energy particles originating from sources throughout the Milky Way and beyond, accelerated by supernovae and other energetic astrophysical events. The Moon also has no meaningful atmosphere. The lunar exosphere, the extremely tenuous layer of gas at the lunar surface, has a pressure of approximately 3 × 10 to the -15 atmospheres. This is not an atmosphere in any sense that provides radiation shielding. It is essentially vacuum. A lunar habitat would be exposed to essentially the same radiation environment as a spacecraft in deep space. What does this mean in numbers? An astronaut on the lunar surface receives approximately 380 millisieverts of radiation per year from galactic cosmic rays and solar radiation combined. For context, the annual radiation limit for radiation workers in the United States is 50 millisieverts per year. The career radiation limit for NASA astronauts is approximately 600 millisieverts, designed to limit lifetime cancer risk increase to 3%. A lunar resident would approach this career limit in less than 2 years. This is a significant problem. It is not insurmountable. Adequate shielding can reduce the radiation dose substantially. Underground habitats, regolith-covered structures, or water-filled walls can provide meaningful shielding. But the lunar radiation environment requires active engineering solutions just to make long-term residence survivable. Now compare this with Mars. Mars also has no global magnetic field. Like the Moon, it lost its global magnetic field early in its history, approximately 4 billion years ago, when its core cooled and the dynamo that had generated the field stopped working. This is a significant disadvantage compared to Earth. Mars is exposed to solar radiation and galactic cosmic rays in ways that Earth is not. But Mars has an advantage the Moon does not. It has an atmosphere. The Martian atmosphere, 95% carbon dioxide, 2.6% nitrogen, 1.9% argon and traces of other gases, is thin by Earth standards, but it is not negligible as a radiation shield. The surface pressure on Mars averages approximately 600 pascals, compared to Earth's 101,325 pascals. This is less than 1% of Earth's atmosphere. But even this thin atmosphere provides measurable radiation shielding. Measurements made by the Curiosity rover's radiation assessment detector show that the surface radiation on Mars is approximately 180 to 225 millisieverts per year, significantly less than the Moon's approximately 380 millisieverts. The Martian atmosphere provides roughly a factor of 2 reduction in surface radiation compared to the lunar surface. This is a meaningful difference. It does not make Mars safe. 200 millisieverts per year is still far above safe limits for indefinite habitation. But it makes Mars less dangerous than the Moon from a radiation perspective. There is also a second radiation-related difference that is less often discussed. On the Moon, there is no protection from solar particle events, sudden bursts of high-energy particles emitted during solar flares and coronal mass ejections. These events can deliver radiation doses of hundreds of millisieverts in a matter of hours, potentially lethal doses in extreme events. The 1972 solar particle event, one of the largest ever recorded, occurred between Apollo 16 and Apollo 17. Had astronauts been on the lunar surface during this event, they would have received a potentially fatal radiation dose. Mars provides somewhat more protection from solar particle events because its thin atmosphere absorbs some of the incoming particles. The protection is not complete. A severe solar particle event on Mars could still deliver dangerous radiation doses at the surface. But the atmosphere provides a factor of 2 to 3 reduction in dose for typical events. Additionally, the curvature of Mars means that during a solar particle event, you can potentially go below ground, into a lava tube, a cave, or a sufficiently deep regolith shelter, and wait it out. The Martian regolith also provides shielding. A meter of Martian soil provides significant protection from solar particle events. None of this makes Mars a radiation paradise. A Mars resident is still receiving radiation doses far above safe limits on Earth. But the comparison with the Moon is stark. The Moon is worse on every metric of radiation protection. No magnetic field, no atmosphere, no protection from solar particle events beyond whatever shielding you can build or dig. Let us now talk about the second major difference: dust. Lunar dust is one of the most significant engineering and health challenges of Moon exploration. It is not obvious from a distance why dust would be a major problem. We have dust on Earth. It is annoying. It clogs filters and dirties surfaces, but it is manageable. Lunar dust is different in character from terrestrial dust in ways that make it fundamentally more dangerous. The key difference is that lunar dust has never been exposed to weathering. On Earth, geological processes, wind, water, chemical reactions, wear down the sharp edges of particles over time. Rocks are ground into soil. Soil particles are tumbled and smoothed. Terrestrial dust is typically made of rounded, relatively smooth particles that do not stick aggressively to surfaces or embed deeply into biological tissue. The Moon has no atmosphere, no water, and no erosion. The particles of lunar regolith, the layer of broken rock and dust covering the lunar surface, are formed primarily by micrometeorite impacts, which shatter rock into tiny fragments without any subsequent weathering. The result is particles with extremely jagged, irregular, glassy edges, sharp at the microscopic scale in ways that terrestrial particles are not. These particles are electrostatically charged. The lunar surface is bombarded by the solar wind, which strips electrons from atoms and charges the regolith. Lunar dust clings to everything: spacesuits, equipment, sensors, windows, with a tenacity that made it a significant operational problem for Apollo astronauts during their brief stays. Within hours of EVA, spacesuits were coated in grey dust that was extraordinarily difficult to remove. For long-term residents, this is a serious health concern. The sharp, jagged particles of lunar dust are highly reactive chemically because their freshly fractured surfaces have never been passivated by exposure to oxygen or water. If inhaled, they would be extremely damaging to lung tissue, more damaging than terrestrial dust particles of similar size. Studies of returned Apollo samples suggest that lunar dust could cause a condition similar to silicosis, a progressive, debilitating lung disease caused by inhalation of fine silicate particles, but potentially more severe because of the unusual reactivity of the lunar material. There is also the problem of dust mobility. On Earth, particles settle quickly because of gravity and air resistance. On the Moon, electrostatically charged dust can levitate, suspended above the surface by electrostatic repulsion from the similarly charged ground. Dust can penetrate into equipment through gaps too small to be visible. It can coat solar panels, reducing their efficiency. It can embed in the moving parts of machinery, causing wear and failure. The Apollo experience showed that even 3 days on the lunar surface produced significant dust contamination of equipment. Astronauts reported that by the end of even brief lunar surface stays, the interiors of spacecraft were noticeably grey. The smell of lunar dust, described by astronauts as a sharp, acrid scent, like gunpowder or spent matches, is the smell of highly reactive, freshly fractured silicate surfaces. For a permanent lunar settlement, dust management would be an ongoing, resource-intensive challenge with no complete solution. You cannot eliminate the dust. You can manage it. Airlocks designed to minimize dust entry, dust removal systems for spacesuits and equipment, filtration systems for habitat air. But the dust is always there, always problematic, always potentially dangerous. Now compare with Mars. Mars also has dust. Martian dust storms can be spectacular. The 2018 global dust storm covered the entire planet and blocked enough sunlight to permanently disable the solar-powered Opportunity rover. Martian dust is a significant operational concern. But Martian dust has been weathered. Mars has an atmosphere, and although that atmosphere is thin, it is enough to weather dust particles over billions of years. Wind erosion on Mars produces particles that are more rounded and less sharp-edged than lunar dust. Mars also has more complex surface chemistry. Perchlorates and other reactive compounds in the soil are a health concern, but the particles themselves are not as physically damaging as lunar dust. Martian dust also behaves differently because Mars has an atmosphere. Dust settles in the presence of atmospheric drag. It does not levitate electrostatically the way lunar dust does. It is easier to contain, easier to manage, easier to clean from surfaces. The dust problem is not absent on Mars. It is real and requires engineering solutions, but it is qualitatively less severe than the lunar dust problem. Let us now talk about the third major difference, the day-night cycle. The Moon rotates very slowly relative to Earth. A lunar day, one complete rotation relative to the Sun, takes approximately 29.5 Earth days. This means that any given location on the Moon experiences approximately 2 weeks of continuous sunlight, followed by approximately 2 weeks of continuous darkness. This is a profound engineering challenge. During the 2 weeks of lunar day, temperatures at the equator reach approximately 127 degrees Celsius, hot enough to boil water. During the 2 weeks of lunar night, temperatures drop to approximately minus 173 degrees Celsius, cold enough to freeze carbon dioxide. The temperature swing over one lunar day-night cycle is approximately 300 degrees Celsius. This is an extreme thermal environment requiring continuous active thermal management. Solar power, the most practical energy source for planetary surfaces, is deeply problematic in this environment. For 2 weeks at a time, there is no sunlight to power solar panels. Any solar-powered lunar settlement would need either enormous battery storage capacity to survive 2 weeks of darkness, or nuclear power, or some other energy source that does not depend on sunlight. The extreme cold of lunar night also creates material stress problems. Equipment subjected to repeated cycles of 300-degree temperature swings undergoes thermal fatigue, expansion and contraction cycles that stress materials and can cause cracks, seal failures, and structural problems over time. Seals that work at 127 degrees Celsius may fail at minus 173 degrees, and vice versa. Lubricants that work in one temperature regime may solidify or decompose in the other. There is a partial solution to this problem. The lunar poles, particularly regions near the lunar south pole, include areas of near-permanent sunlight where crater rims are illuminated by the low-angle sun for more than 80% of the lunar year, while nearby craters contain regions of permanent shadow where temperatures stay near minus 200 degrees Celsius and water ice is preserved. A settlement at the right polar location could receive nearly continuous sunlight and avoid the worst of the day-night cycle. This is why most serious lunar settlement proposals locate the base at the South Pole. But even the best polar sites do not provide continuous sunlight. There are brief periods of darkness, and the proximity to permanently shadowed craters means the local environment is extremely cold, even when sunlit. Now compare with Mars. Mars rotates with a period of 24 hours and 37 minutes. Almost exactly the same as Earth. The Martian day, called a sol, is only 37 minutes longer than an Earth day. This means that any location on Mars experiences a day-night cycle very similar in rhythm to Earth. Sunrise and sunset each sol, with a relatively predictable pattern of light and dark. The temperature range on Mars is challenging. Surface temperatures range from about minus 80 degrees Celsius at the poles in winter to about 20 degrees Celsius on warm summer afternoons near the equator. But the diurnal temperature swing at any given location is much smaller than the lunar range. At the Curiosity rover's location in Gale Crater, typical temperature swings from day to night are roughly 70 to 100 degrees Celsius, significant but far less extreme than the Moon's 300-degree swings. This means solar power works on Mars in a way it does not work on the Moon. You get power during the day and need storage or alternative sources at night, just as you do on Earth. The engineering is much more manageable. Thermal cycling is less extreme. Equipment is not stressed by 300-degree temperature swings. This is a significant advantage for Mars. The 24-hour-plus day cycle of Mars is one of the ways Mars is more Earth-like, more habitable in the engineering sense than the Moon. Let us now talk about gravity, about the specific and often underappreciated health implications of living in different gravitational fields for extended periods. Earth's gravitational acceleration at the surface is 9.8 meters per second squared, defined as 1 g. The human body is exquisitely calibrated for this environment. Bone density, muscle mass, cardiovascular function, fluid distribution, the vestibular system, all are tuned by evolution to function optimally in 1 g. When humans experience reduced gravity, these systems begin to adapt. In zero gravity, the microgravity environment of the International Space Station, the adaptations are rapid and significant. Bone density decreases at a rate of approximately 1 to 2% per month. Muscle mass decreases. The heart, no longer working against gravity to pump blood upward, reduces in size and efficiency. Fluids shift toward the upper body, creating the characteristic puffy-faced appearance of ISS astronauts and increasing intracranial pressure in ways that can damage vision. These changes are well documented from decades of ISS research. The question relevant to our comparison is what happens at the intermediate gravity levels of the Moon and Mars, levels between 0 and Earth's 1 g. The Moon's surface gravity is approximately 0.165 g, 1/6 of Earth's. Mars's surface gravity is approximately 0.375 g, about 3/8 of Earth's. The critical question is whether there is a minimum level of gravity sufficient to maintain long-term human health, and if so, where that threshold is. The honest answer is that we do not know. The ISS research program has extensively studied zero-gravity physiology. We have brief data points from the Moon. The Apollo astronauts spent a maximum of 3 days on the lunar surface, too short to detect the long-term effects of lunar gravity. We have no data at all on human physiology at Mars gravity because no human has ever experienced it. What we can say is this: the physiological changes seen in microgravity are driven primarily by the absence of mechanical loading, the absence of forces on the body that stimulate bone and muscle maintenance. If the Moon's 0.165 g provides only 1/6 the mechanical loading of Earth, it may not be sufficient to maintain bone and muscle health over long periods. The body may continue to lose bone and muscle in lunar gravity at rates slower than 0 g, but faster than would be acceptable for indefinite habitation. Mars gravity at 0.375 g is more than twice the Moon's. It provides substantially more mechanical loading. Whether 0.375 grams is sufficient for long-term health is unknown, but the higher gravity of Mars makes it more plausible that Martian residents could maintain reasonable health without continuous countermeasures than lunar residents at 1/6 gravity. This is a significant advantage of Mars over the Moon for long-term habitation. Not a certainty. We genuinely do not know if 0.375 g is adequate, but a more plausible prospect for sustainable human health. There is also a psychological dimension to the gravity question. The lunar gravity of 0.165 g is low enough to allow extraordinary physical feats. The Apollo astronauts could jump to considerable heights and move in ways impossible on Earth. But it is also low enough that every physical movement feels profoundly alien. Balance systems tuned for 1 g receive incorrect signals in 0.165 g. Fine motor control is affected. The experience of moving in lunar gravity, while fascinating for brief visits, may become deeply disorienting and physiologically damaging over months and years. Mars gravity, being more than twice lunar, would feel different but less alien. A person weighing 70 kilograms on Earth would weigh approximately 26 kilograms on Mars, substantially lighter than on Earth, but not as profoundly different as the 11.5 kilograms they would weigh on the Moon. The subjective experience of living in Martian gravity, while novel, would be closer to the human norm. Let us now talk about something that is less often discussed, but that may be one of the most significant long-term challenges of lunar habitation: the psychological and circadian implications of the lunar day-night cycle. Human physiology runs on a circadian rhythm, a roughly 24-hour internal clock governing sleep, alertness, hormone production, body temperature, and numerous other biological processes. This clock is synchronized primarily by light exposure, specifically by changes in light intensity and spectrum that occur naturally with the rising and setting of the sun. On Earth, the 24-hour light-dark cycle and the circadian rhythm are naturally synchronized. The body knows when to be awake and when to sleep based on light cues that have been consistent throughout evolutionary history. On the Moon, the 29.5-day cycle of light and dark provides no useful circadian cues. A lunar settlement at the equator would experience 14 days of daylight followed by 14 days of darkness, periods completely divorced from the human 24-hour rhythm. Even a polar settlement with near-continuous sunlight would lack the light-dark cycling needed to synchronize circadian clocks. Circadian disruption is a serious medical problem. Chronic misalignment of the circadian clock with the light-dark environment, as experienced by shift workers and frequent flyers crossing multiple time zones, is associated with increased risk of cardiovascular disease, metabolic disorders, immune dysfunction, cognitive impairment, and cancer. Long-term circadian disruption at the scale that lunar habitation would impose represents an understudied but potentially significant health risk. Lunar residents would need to create artificial light environments inside habitats that simulate a 24-hour day-night cycle, isolated from the external environment. This is achievable with current technology, but it adds another layer of engineering complexity and another system that must function reliably to maintain resident health. Mars, again, has an advantage. The Martian sol of 24 hours and 37 minutes is close enough to the human 24-hour circadian rhythm that it might be possible to naturally synchronize with the Martian day. The 37-minute excess each day would gradually accumulate, as it does for people who naturally tend to drift to slightly longer than 24-hour cycles. But research on people living on Martian time during rover missions suggests that most people can adapt to the Martian sol without major disruption. The light-dark cycle on Mars, even filtered through the Martian dust and atmosphere, provides real circadian cues that can be used to synchronize biological clocks. This is a genuine advantage of Mars. Not definitive, we do not have long-term data on humans living on Martian sol schedules, but suggestive that the Martian day cycle is more compatible with human physiology than the lunar cycle. Let us now talk about one more dimension of the comparison, about the resources available at each destination and what those resources mean for the long-term sustainability of a human presence. Self-sufficiency is the ultimate goal for any permanent off-Earth human presence. A settlement that depends entirely on supply missions from Earth is not a settlement. It is an outpost, vulnerable to supply chain disruptions, dependent on the continued will and resources of the sending civilization, fundamentally limited in the number of people it can support. A truly self-sufficient settlement needs the ability to produce its own food, water, oxygen, fuel, and building materials from local resources. The question is what each world provides for this purpose. Water is the most fundamental resource. Humans need water to drink, to grow food, and to produce oxygen through electrolysis. Water can also be split into hydrogen and oxygen to produce rocket fuel, making it doubly valuable for any settlement with aspirations of continued space travel. Both the Moon and Mars have water. On the Moon, water ice is confirmed in permanently shadowed craters near the poles, deposited over billions of years by comets and asteroid impacts. The total quantity is uncertain, but potentially substantial. On Mars, water ice is abundant. The polar ice caps contain enormous quantities of water ice, and radar observations suggest water ice also exists in the subsurface at lower latitudes. The difference is accessibility. Lunar water ice is in permanently shadowed craters at temperatures near -200 degrees Celsius, some of the coldest places in the solar system. Extracting this ice requires operating equipment in extreme cold in the permanent shadow of crater interiors, technically challenging. Martian water ice, while also requiring extraction effort, is more accessible in some regions and exists in a less extreme environment. Atmosphere is another resource comparison worth making. The Martian atmosphere, while too thin to breathe and too thin to provide meaningful pressure for unprotected humans, is a resource. Carbon dioxide can be chemically processed to produce oxygen and carbon monoxide. The MOXIE instrument on the Perseverance rover has already demonstrated this, producing oxygen from Martian atmospheric carbon dioxide. Nitrogen in the Martian atmosphere can provide the inert gas component of a breathable air mixture. The Moon has no atmosphere to use as a resource. Oxygen on the Moon must come from breaking apart oxygen-bearing minerals in the regolith. Possible, but requiring more energy than extracting oxygen from carbon dioxide. For construction materials, both worlds offer similar resources: rock, metals, and in the case of the Moon, aluminum-rich regolith. Mars has the advantage of a more chemically complex surface, richer in clay minerals and other compounds, but both worlds could in principle supply basic construction materials from local sources. The overall picture on resources is that Mars offers modestly better conditions for self-sufficiency, easier water access, an atmosphere that can be chemically processed, better solar energy conditions. Neither world is resource-rich by human standards. Both would require enormous engineering effort to achieve meaningful self-sufficiency. But Mars presents a somewhat more favourable starting point. Let us now pull back and look at the full picture, at the aggregate comparison between lunar and Martian habitation across all the dimensions we have discussed. Radiation. The Moon provides essentially no protection, no magnetic field, no atmosphere. Surface radiation is approximately 380 millisieverts per year. Mars provides some protection through its thin atmosphere. Surface radiation is approximately 180 to 225 millisieverts per year. Advantage Mars by approximately factor of 2. Dust. Lunar dust is extremely fine, extremely sharp-edged, extremely reactive, electrostatically charged, and persistent. It is a health and engineering challenge with no complete solution. Martian dust is a serious operational challenge, but is weathered, less sharp, less reactive, and more manageable. Advantage Mars, day-night cycle. The Moon experiences 14-day periods of sunlight and darkness with 300-degree temperature swings. Solar power is impractical at most locations. Circadian disruption is a significant concern. Mars experiences a 24-hour, 37-minute sol with manageable temperature swings. Solar power works normally. Circadian adaptation is possible. Advantage Mars significantly. Gravity. The Moon's 0.165 g may be insufficient for long-term human health. Mars's 0.375 g provides more mechanical loading. Neither is confirmed safe for indefinite habitation, but Mars is more plausible. Advantage Mars. Resources. Both worlds have water ice. Mars has an atmosphere that can be chemically processed for oxygen. Mars is slightly more resource favorable for self-sufficiency. Advantage Mars modestly. Distance and accessibility. The Moon is 3 days away and allows near real-time communication. Mars is 6 to 9 months away and communication delays reach 44 minutes. Advantage Moon dramatically for emergency response and supply logistics. Protection from emergencies. The Moon's proximity allows emergency evacuation within days. Mars offers no such option. A medical emergency on Mars cannot be rescued from Earth on any relevant timescale. Advantage Moon dramatically. The picture that emerges from this comparison is nuanced. The Moon has enormous advantages in terms of proximity, accessibility, and emergency response capability. These are not trivial. The ability to respond to emergencies, to resupply, to evacuate if necessary. These are the advantages that make the Moon an attractive first step for permanent human presence beyond Earth. But for the specific question of long-term habitability, for the question of what it is like to actually live somewhere for months or years, the Moon is in several important respects a more hostile environment than Mars. The radiation environment is worse. The dust is more dangerous. The temperature extremes are more severe. The day-night cycle is more disruptive. The gravity is lower and potentially less compatible with long-term health. This is the counterintuitive insight at the heart of tonight's comparison. Closer does not mean safer. More accessible does not mean more habitable. The Moon is easier to reach but harder to live on. Mars is harder to reach, but in the specific physical and physiological senses we have examined, somewhat more hospitable once you are there. Both worlds will require extraordinary engineering effort, extraordinary technological capability, and extraordinary human resilience to make long-term habitation possible. Neither is close to the experience of living on Earth. Both present dangers that kill quickly if systems fail, and more slowly if specific chronic hazards are not managed. But the comparison is real, the differences matter. And understanding them correctly, understanding specifically why the Moon presents the challenges it does and how they compare to Mars, is essential for any serious planning of permanent human presence beyond Earth. Let us talk about something that requires a deeper look, about the specific engineering solutions that have been proposed for the most dangerous aspects of lunar habitation, and about why each solution introduces its own complications. Start with radiation shielding. The most straightforward approach to reducing radiation exposure on the Moon is to put something massive between the residents and space. Mass is the fundamental radiation shield. The more material between you and the radiation source, the more radiation is absorbed before it reaches you. On Earth, our atmosphere provides about 10 meters of water-equivalent shielding. The ISS provides roughly 20 to 30 grams per square centimeter of shielding from its hull, enough to reduce radiation somewhat, but nowhere near enough for indefinite habitation. On the Moon, the most practical massive shielding is the regolith itself, the layer of broken rock covering the surface. A meter of lunar regolith provides roughly 250 grams per square centimeter of shielding, which would reduce the radiation dose to lunar residents by a factor of several. 2 to 3 meters of regolith overhead would bring the annual radiation dose inside a lunar habitat to roughly comparable levels with ISS residents, still above safe limits for indefinite habitation, but substantially reduced from the unshielded surface dose. This sounds manageable. The Moon has essentially unlimited regolith. You can pile it on top of habitats, build berms around structures, construct underground facilities. But there are complications. First, constructing underground or regolith-covered habitats on the Moon requires construction equipment, energy, and engineering capability that does not yet exist in lunar form. Moving regolith is energy-intensive. Compacting it adequately to prevent collapse requires either specialized equipment or careful engineering. The structural loads on habitat roofs covered by meters of regolith are substantial and require robust, well-designed structures. Second, The regolith itself is not a complete solution for all radiation types. Galactic cosmic rays consist of very high-energy particles that can penetrate substantial amounts of material. As these particles pass through material, they produce secondary radiation, a shower of lower-energy particles generated by the interaction of the primary cosmic ray with the shielding material. This secondary radiation can, in some configurations, exceed the dose from the primary cosmic ray if the shielding is not optimally designed. The optimal radiation shield is not simply the thickest possible material. It is a carefully designed combination of materials chosen to maximize primary absorption while minimizing secondary production. Typically, hydrogen-rich materials like water or polyethylene are most effective per unit mass, followed by aluminium, with heavier materials becoming less efficient due to secondary production. A lunar habitat shielded by regolith would need to be carefully designed to account for secondary production, and might need additional internal shielding of more optimal materials. Third, even optimally shielded habitats do not eliminate the solar particle event problem. During a major solar particle event, the dose rate at the unshielded lunar surface can reach levels causing acute radiation sickness within hours. Residents in adequately shielded habitats would be protected, but the design of those habitats must account for the worst-case solar particle events that occur unpredictably and can be larger than the largest events in the observational record. These complications do not make the radiation problem insoluble. They make it expensive, technically demanding, and requiring solutions that add mass, complexity, and cost to lunar habitation. Let us now talk about the dust problem in more depth, about the specific mechanisms by which lunar dust causes problems, and about the engineering approaches being developed to address them. The electrostatic charge on lunar dust is the root of most of the problems. On Earth, dust particles acquire and lose charge continuously through contact with humid air, through interaction with other particles, through rain and water. The charge dissipates rapidly. On the Moon, in the absence of atmosphere and with direct bombardment by solar wind, dust particles become highly charged and stay charged. This charged dust is attracted to anything at a different electrical potential, including spacesuit fabric, optical surfaces, equipment panels, and the interior surfaces of habitats. It adheres with forces that cannot be simply brushed away. The fine particles penetrate into fabric weaves, into equipment joints, into breathing apparatus. Once inside a habitat, the dust becomes airborne and is difficult to filter completely. Several engineering approaches have been proposed. Electrostatic dust shields, arrays of electrodes that create a traveling electric field across a surface designed to levitate and repel charged dust particles, have been tested in laboratories and show promise for keeping optical surfaces and solar panels dust-free. They require power to operate and have not yet been tested at the scale and in the conditions of actual lunar surface operations. Spacesuit materials designed to be less electrostatically attractive to dust are being developed. Surface treatments that reduce the tendency of dust to adhere. Air filtration systems with high enough efficiency to capture particles of the size range found in lunar dust. None of these is a complete solution. The fundamental issue that the lunar regolith consists of extraordinarily fine, sharp, reactive particles that will be disturbed by any human activity near the surface cannot be engineered away. It can be managed, but managing it requires ongoing effort, reliable systems, and careful procedures that add to the operational complexity of lunar habitation. The health risk from dust inhalation is perhaps the most concerning long-term issue. Apollo astronauts spent days on the Moon and returned to Earth for medical observation. If any of them developed lung damage from dust inhalation, the long latency period for dust-related lung disease means it might not manifest for years to decades. The long-term health effects of brief Apollo dust exposure are still being studied. For permanent lunar residents who would inhale trace amounts of lunar dust continuously over years, the risk profile is entirely unknown. Studies of returned Apollo samples show that lunar dust particles have irregular, glassy surfaces similar to fine volcanic ash, and fine volcanic ash is known to cause silicosis when chronically inhaled. Silicosis is progressive, irreversible, and potentially fatal. There is no direct evidence that lunar dust causes the same disease, but the physical similarity is concerning enough that dust inhalation mitigation is considered a critical requirement for any permanent lunar settlement. Let us now talk about something that is rarely given sufficient weight in comparisons between lunar and Martian habitation: about the psychological dimension of living in each environment. Humans are not simply biological machines optimized for a particular set of physical parameters. We are also psychological beings who require certain kinds of environment to function well. Environments that provide meaningful work, social connection, aesthetic experience, a sense of connection to the larger world. The psychological environment of a lunar settlement would be distinctive in ways that deserve consideration. The view from the moon is spectacular in one sense. The Earth hanging in the lunar sky is one of the most profound sights available to any human, and the lunar landscape has its own stark beauty. But the landscape is also profoundly monotonous. Grey dust, grey rock, black sky, no weather, no change. The moon has no weather because it has no atmosphere. No clouds, no rain, no wind, no seasons. The landscape looks the same today as it did 1 million years ago, and will look the same 1 million years from now. This monotony is not trivial. Environmental psychology research shows that humans perform better, feel better, and maintain better mental health in environments with variety, natural complexity, and sensory richness. The minimum sensory environment on the moon, inside a shielded habitat with no natural light cycles, surrounded by grey sameness, would likely require significant artificial augmentation to maintain psychological well-being. Mars, while also profoundly hostile to human life, has more visual variety than the moon. The thin Martian atmosphere produces weather: dust devils, dust storms, frost, haze. The sky changes colour through the day. The landscape, while monochromatic, has geological features of striking complexity: ancient river channels, vast canyon systems, towering volcanoes, polar ice caps. Mars has seasons, as its axial tilt produces changing conditions over its year. The landscape has variety in a way the moon's does not. This is not to say Mars is psychologically comfortable. The knowledge that you cannot step outside without a spacesuit, that the environment will kill you in seconds without protection, that you are separated from Earth by months of travel and tens of minutes of communication delay. These realities would create profound psychological stress for any Mars resident. But Mars at least provides an environment with more natural variation, more geological interest, and more of the qualities that human psychology responds to as interesting rather than merely threatening. Let us now talk about something specific and concrete, about what daily life in a lunar settlement would actually look like, and how the specific challenges we have discussed would manifest in day-to-day experience. A person living in a near-term lunar settlement would spend most of their time inside a habitat, a pressurized, radiation-shielded structure containing living quarters, laboratories, exercise facilities, food production systems, and life support systems. Going outside would require putting on a spacesuit, a process taking 20 to 45 minutes, involving careful safety checks and adding immediately to the accumulated dust contamination of the suit that must then be managed on return. Exercise would be a daily requirement, not for enjoyment, but for survival. In the Moon's 0.165 G, bone and muscle loss would begin immediately without vigorous countermeasures. Current ISS protocols require approximately 2 hours of exercise per day for astronauts in zero gravity. Lunar gravity, being higher than 0 g but still very low, would likely require substantial daily exercise to mitigate bone and muscle loss. Exercise regimens that consume time and energy that would otherwise go to the primary mission. The rhythm of the lunar day, 14 days of light, 14 days of dark, would be largely invisible from inside a shielded habitat, but its effects would be felt through temperature fluctuations in external systems, through changes in the performance of any external solar panels, and through the psychological knowledge of being in permanent darkness for 2 weeks at a time. Communication with Earth would be essentially real-time, only 1.28-second delay each way. This is a significant psychological advantage compared to Mars. A lunar resident could have a real conversation with friends and family. They could receive and respond to Earth news with only seconds of delay. The sense of connection to Earth, while still separated by the physical reality of space, would be much stronger than on Mars. The work of a lunar settlement would be primarily scientific. Geological surveys, sample collection, astronomical observations benefiting from the stable lunar surface and lack of atmosphere, and the technical work of maintaining the settlement itself. As a settlement matured, in situ resource utilization, extracting water from polar ice, processing regolith for construction materials and oxygen, would become a major activity. This picture is a reasonable extrapolation of near-term lunar habitation. It is not comfortable or easy, but it is potentially achievable with technology not fundamentally different from what exists today. Let us now talk about something that connects the Moon-Mars comparison to the broader question of why we are interested in going to either place at all. The case for human presence on the Moon rests primarily on 3 arguments. The first is scientific. The Moon is a geological archive of the early solar system. Its ancient, uneroded surface preserves a record of the first billion years of solar system history that has been erased on more geologically active worlds. The far side of the Moon, permanently shielded from Earth's radio emissions, offers a uniquely quiet environment for low-frequency radio astronomy impossible from Earth. The second is practical. The Moon is close enough to Earth to serve as a testing ground for technologies, procedures, and human physiological responses needed for deeper space exploration. If something goes wrong on the Moon, help can arrive within days. The Moon as a proving ground reduces the risk of sending humans to Mars by allowing mistakes to be made and corrected in a more forgiving environment. The third is resource access. The water ice in lunar polar craters, if it can be economically extracted, could provide propellant for spacecraft continuing outward in the solar system, potentially making the Moon a refueling station that reduces the cost of Mars missions and beyond. The case for Mars rests on different but overlapping arguments. Mars is the most Earth-like world in the solar system. It has the highest probability of having once harbored life, and possibly still harboring microbial life in subsurface environments where liquid water might persist. Mars, ultimately, is the destination most seriously discussed for permanent human colonization, for the establishment of a self-sustaining human civilization beyond Earth. The Moon and Mars are thus not really competing destinations. They are sequential steps. The Moon to learn, to test, to develop technology and experience. Mars to settle, to establish a permanent presence, to begin the long process of becoming a multi-planetary species. Understanding the specific dangers of each, understanding why the Moon is in several respects more dangerous than Mars despite being much closer, is essential for planning this sequence correctly. For building habitats that provide adequate shielding at the right locations, for developing dust mitigation technologies before they are needed at scale, for designing exercise and medical protocols for gravity levels we have never sustained humans in, for planning day-night energy systems adequate for 2 weeks of darkness. The work is concrete, the engineering is real, the dangers are specific and verifiable, and addressing them correctly will determine whether permanent human presence beyond Earth is something that becomes part of the human story or remains forever a dream deferred. Let us now talk about something that is often missing from popular discussions of lunar habitation, about the specific medical challenges that are unique to the Moon and that would require new medical protocols, new technologies, and possibly new treatments. Medical care in a lunar settlement would operate in a context fundamentally different from medicine on Earth. The reduced gravity environment changes how many medical procedures work. Intravenous fluids behave differently when gravity does not consistently pull them downward. Wound healing may be affected by the altered fluid distribution in low gravity. Orthopedic surgery, repair of broken bones, involves principles developed entirely for Earth gravity. How fractures heal in 1/6 gravity is not well understood. The radiation environment creates chronic low-level DNA damage that accelerates cancer risk and may have other effects that manifest over years to decades. Managing this requires monitoring, radiation dosimetry, regular health screening, and potentially treatments that do not yet exist to repair or compensate for chronic radiation damage. The dust creates respiratory risk that requires ongoing monitoring and potentially treatment of early silicosis-like conditions before they progress to disabling disease. Current silicosis treatment on Earth is supportive. There is no cure. Preventing dust exposure is the primary medical strategy, but perfect prevention in a lunar environment may not be achievable. Mental health care in a small, isolated, highly stressed community is another significant challenge. The psychological stress of the lunar environment, the confinement, the monotony, the dust, the constant awareness of the hostile environment beyond the habitat walls, the separation from Earth despite real-time communication, would create conditions where mental health problems are expected. Psychiatric care, including pharmaceutical treatment, must be available. Group dynamics in small, isolated communities are prone to specific kinds of conflict and dysfunction that require skilled management. Emergency medicine on the Moon would also be distinctive. Trauma surgery in a pressurized habitat is possible, but requires equipment and expertise that must be on site. You cannot call for a surgeon from Earth. Intensive care capability, ventilators, monitoring equipment, pharmaceuticals must be present and maintained. The margin for medical error is smaller because evacuation to a better equipped facility, while theoretically possible, takes time and carries its own risks. Mars presents similar medical challenges in most of these domains, but the inability to evacuate in any timely sense makes them even more acute. On the Moon, a severe medical crisis that cannot be managed locally could in principle result in emergency evacuation within a week. On Mars, there is no emergency evacuation. The medical capability on Mars must be sufficient to handle any conceivable crisis without external help. In this respect, medical self-sufficiency, Mars demands more than the Moon. The Moon's proximity provides a safety net, however imperfect, that Mars does not. This is the dimension in which the Moon's advantage in distance is most clearly felt as a habitation advantage, rather than merely a logistical one. Let us now talk about the specific question of what the Moon and Mars look like as destinations for the first truly permanent human settlement, for a community of people intending to remain indefinitely rather than rotating through on fixed tours. A rotating outpost, where individuals serve tours of duty and are replaced by fresh arrivals, is not the same as a permanent settlement. A rotating outpost can maintain human presence at a location while managing health risks through tour length limits, evacuation procedures, and the assumption that residents will return to Earth for recovery and medical monitoring. A permanent settlement, a community where people intend to stay, where children might be born, where individuals commit to remaining for the rest of their lives, faces a different category of challenges. The health effects of permanent residence in 1/6 lunar gravity are unknown. We have no data on what happens to a human body over decades in 0.165 g. We do not know if bone loss stabilizes at a new equilibrium or continues until bones become non-functional. We do not know if the cardiovascular adaptations to low gravity are reversible after years of residence. We do not know if vision problems associated with low gravity fluid shifts, stabilize, or progress. We do not know if permanent residence in a high radiation environment is survivable even with mitigation. For children born on the Moon, children who have never experienced Earth's 1G, the developmental effects of growing up in 1/6 gravity are completely unstudied. Would their cardiovascular systems develop normally? Would their skeletons develop adequate strength? Would they be able to visit Earth if they chose to? These are not hypothetical questions to answer eventually. They are questions that must be answered before the first permanently inhabited lunar community can be responsibly established. The same questions apply to Mars, where the gravity is higher but still well below Earth's. But Mars's higher gravity makes the answers marginally more likely to be favourable. A child growing up in 0.375 g Mars gravity would experience more physical loading than one in 0.165 g lunar gravity. The developmental effects, while still unknown, are more plausibly within the range compatible with human health. These considerations suggest that the transition from outpost to permanent settlement, from a place where people visit to a place where people live, will require a research program more extensive than anything yet planned. Decades of systematic study of human physiology at reduced gravity in high radiation environments in extreme isolation over timescales of years to decades. The Moon offers the opportunity to conduct this research in the relatively accessible environment of 3 days' travel from Earth. Whatever we learn there about dust, about radiation, about gravity, about psychology, about medicine, will be applicable to Mars and will increase the probability that Mars settlement, when it comes, is sustainable rather than lethal. This is the most important practical argument for lunar habitation before Martian habitation. Not that the Moon is a pleasant place to live. It is less pleasant than Mars in several respects, but that the Moon is where we can learn at manageable risk what we need to know to survive on Mars. The Moon as school, Mars as the destination. The dangers of the Moon are real. They are more serious in several respects than the dangers of Mars. Understanding them precisely, knowing exactly what the radiation environment is, exactly what the dust does to lungs and equipment, exactly what prolonged low gravity does to human physiology, is the work that must be done before either world can become a true home. The Moon is where that work begins. Let us talk about something that has not yet been adequately addressed, about the specific geological nature of the Moon and what it means for the physical stability of any structures built there. The Moon is geologically quiet by Earth standards. It has no active volcanism, no plate tectonics, no erosion from water or wind. In this sense, the lunar surface appears stable, a landscape essentially unchanged for billions of years, offering a solid foundation for construction. But the Moon experiences moonquakes, and moonquakes are in some ways more concerning than earthquakes for human habitation. Seismometers deployed by Apollo missions recorded 4 types of moonquakes. Shallow moonquakes are the most concerning. They occur at depths of 20 to 30 kilometers and can reach magnitudes of 5.5 on the Richter scale. These are not trivial events. A magnitude 5.5 earthquake on Earth causes significant structural damage to unreinforced buildings. What makes lunar moonquakes distinctively dangerous compared to terrestrial earthquakes is their duration. Earthquakes last seconds to perhaps a minute or two. Moonquakes, because the Moon has no water in its rock to dampen seismic waves, can last for 10 minutes or more. The seismic energy bounces around inside the Moon for extraordinary periods before dissipating. The Apollo seismic data famously showed that when the spent Apollo 12 lunar module ascent stage was deliberately crashed into the Moon, the seismic signal reverberated for 55 minutes, causing mission controllers to describe the Moon as ringing like a bell. For a pressurized habitat and its seals, a 10-minute structural vibration event is significantly more challenging than a brief, sharp shock. The structural design requirements for lunar habitats must account for this specific seismic environment, not just peak forces, but sustained vibration over many minutes, potentially at frequencies that could drive resonance in structural elements or fatigue seals and connections. At the lunar poles, where most serious settlement proposals are located, there is an additional geological consideration. The permanently shadowed craters containing water ice are at the poles precisely because they never see sunlight, and temperatures inside them can reach -200 degrees Celsius. The craters immediately adjacent to the illuminated ridgetops that make good settlement sites are subject to extreme temperature gradients, from near absolute zero in the shadows to relatively warmer temperatures in the sunlight a few hundred meters away. These temperature gradients drive thermal stresses in the regolith. Over billions of years, the constant thermal cycling at crater rims has fractured the regolith in ways that may create unstable surfaces. Construction on crater rims, which is where the near-permanent sunlight is, requires understanding the structural properties of this thermally cycled regolith, which are poorly characterized. Lava tubes, subsurface tunnels created by ancient volcanic activity, have been identified on the Moon using data from lunar orbiting spacecraft. These structures, which can be hundreds of meters wide and kilometers long, could provide natural radiation shielding and thermal stability for lunar settlements. The intact roof of a sufficiently deep lava tube provides meters of rock shielding while maintaining a stable internal temperature unaffected by the extreme surface thermal cycling. Several candidate lava tube entrances have been identified on the Moon, including a pit in the Marius Hills region approximately 65 meters in diameter and possibly 80 to 90 meters deep. Whether these pits actually lead to accessible intact tube systems, rather than simply being isolated collapse pits, requires surface investigation that has not yet occurred. Mars also has lava tubes, substantially larger ones, because the lower gravity of Mars allowed volcanic tubes to form at much larger scales before the roof collapsed under its own weight. Some Martian lava tubes may be wide enough to enclose an entire city. The lower gravity and thicker tube roofs make Martian lava tubes potentially even more attractive as settlement sites than lunar ones. But the critical difference is that we have orbiting spacecraft that have identified specific candidate sites on both worlds, and we have not yet explored any of them at the surface. The detailed geological suitability of any specific site, lunar or Martian, remains to be determined. Let us now talk about something that connects the technical challenges of lunar habitation to the broader question of what it means to design for human life in an environment that is fundamentally incompatible with human existence. Earth life evolved over approximately 4 billion years in a specific set of conditions: specific atmospheric composition, specific pressure, specific temperature ranges, specific radiation levels, specific gravitational field, specific day length, specific access to liquid water. Every organ system in the human body reflects this evolutionary history. Every aspect of human physiology assumes these conditions. The Moon violates nearly every one of these conditions simultaneously. No breathable atmosphere, essentially no pressure, extreme temperatures, high radiation, very low gravity, no water at the surface, a day length incompatible with human circadian biology. In terms of the fundamental parameters of the environment, the Moon is as different from Earth as any place we know in the solar system, in some respects more different than Mars. This is the physical basis for the claim that living on the Moon is more dangerous than living on Mars. Not because the Moon is farther or harder to reach, it is neither, but because the Moon's specific combination of environmental parameters is, on multiple axes simultaneously, more hostile to human biology than Mars. Living on the Moon requires a complete technological substitution of the entire natural environment. Every element of the environment that supports human life must be artificially provided: air, pressure, temperature, water, food, radiation shielding, lighting to substitute for a usable day-night cycle. None of it exists naturally. All of it must be built, maintained, and reliably operated. Living on Mars requires the same technological substitution for air, pressure, and radiation shielding. But it does so in an environment that provides a temperature range less extreme, a day length more compatible with human biology, a gravity more compatible with long-term health, and atmospheric resources that can be used to supplement artificially produced oxygen and nitrogen. This does not make Mars comfortable or safe. It makes Mars a less extreme departure from the conditions human biology requires. Let us now talk about what specifically can be learned from the differences between these two worlds that is relevant to the practical design of habitats and settlement systems. The lunar radiation environment demonstrates that passive shielding, simply being at the surface, is not adequate. Any serious lunar settlement must plan from the beginning for substantial radiation shielding, whether through regolith coverage, underground construction, or a combination. The lesson for Mars is similar but less acute. Mars settlements will also need radiation mitigation, but the thinner requirements leave more design flexibility. The lunar dust problem demonstrates that material compatibility with the surface environment must be planned in detail before deployment. The Apollo program discovered the dust problem through experience. Any future lunar settlement must design specifically for dust management. Airlocks designed for dust containment, suit doffing systems that prevent tracked dust from contaminating habitat interiors, filtration systems designed for the specific size and chemistry of lunar dust, and monitoring systems to track inhalation exposure. The lesson for Mars is that surface material properties must be understood and designed for specifically. Martian perchlorates in the soil present a different set of challenges that must be equally carefully planned. The lunar day-night cycle demonstrates that energy system design must account for the full duration of nights without sunlight. For the Moon, this means 2 weeks. For Mars, it means one night of roughly 12 hours. But also the variability introduced by dust storms that can reduce solar insolation dramatically for weeks to months. Nuclear power, either fission or potentially eventually fusion, is the energy solution most robust to both of these challenges. The kilopower and similar small fission reactor projects are relevant to both destinations. The gravity comparison, 0.165 g on the Moon versus 0.375 g on Mars, demonstrates that the effects of reduced gravity on human physiology must be studied systematically and across a range of gravity levels. The ISS research program has extensively characterized zero-G physiology. Centrifuge experiments on Earth can simulate some aspects of reduced gravity, but actual data at lunar and Martian gravity levels will require time at those locations. The Moon can provide that data for 0.165 g more quickly and with less mission risk than Mars. Each of these lessons, from radiation, dust, day-night cycle, gravity, represents a design requirement for lunar settlement that, once addressed, produces knowledge applicable to Mars settlement design. The Moon is not just a destination. It is a laboratory for learning the specific engineering solutions needed for every world beyond Earth. Let us now talk about the timeline and the practical near-term plans for returning humans to the Moon, about what is actually planned, what the specific challenges of those plans are, and how the hazards we have discussed figure in. NASA's Artemis program aims to return humans to the Moon, the first time since Apollo 17 in December 1972, beginning with the Artemis 3 mission currently targeted for the mid-2020s. The mission would land astronauts near the lunar South Pole for a surface stay of approximately 1 week. 1 week is very different from permanent habitation. The health risks from 1 week of lunar surface exposure, radiation, dust, low gravity, are manageable. The radiation dose from 1 week at the lunar surface is approximately 7 to 8 millisieverts, significant but not acutely dangerous. Dust contamination of spacesuits over 1 week is a concern, but not a health emergency. Bone loss over 1 week is not clinically significant. The Artemis program's ambitions extend beyond brief visits. The Lunar Gateway, a small space station in a near rectilinear halo orbit around the Moon, is planned as a staging post for long-duration lunar surface missions. The gateway itself would provide more radiation shielding than the open lunar surface. Longer surface stays of weeks to months are eventually envisioned. The transition from the Artemis program's near-term visits to a sustained presence, habitats on the surface, crews staying for months, the beginning of a lunar economy, represents a massive step in both capability and investment. Artemis demonstrates that it is possible to send humans to the moon. Building a permanent settlement is an entirely different undertaking. The ESA, JAXA, and other space agencies have proposed concepts for international lunar villages, shared infrastructure at the South Pole supporting multiple nations' activities. These concepts recognize that the scale of investment required for permanent lunar habitation is beyond any single nation's likely commitment and would benefit from international cooperation. China's CNSA has its own lunar ambitions, with planned crewed lunar missions in the 2030s and concepts for a lunar research station at the South Pole in collaboration with Russia. The competitive dynamic between American-led and Chinese-led programs has added urgency to lunar planning that was largely absent in the 2000s and early 2010s. Whether this urgency translates into the sustained investment needed for permanent settlement, investment that must continue for decades through political cycles and budget pressures, remains to be seen. Let us now talk about something more fundamental, about what the specific comparison between lunar and Martian hazards reveals about the general principles of what makes a world habitable. The naive assumption is that habitable worlds are those most similar to Earth in the most obvious ways, rocky, with liquid water, in the habitable zone of their star. This is correct at the broadest scale. But for the specific question of human habitation, not the question of what worlds could support life in general, but the question of what worlds could support human life with foreseeable technology, the relevant parameters are more specific. Gravity in a range compatible with long-term human health. Day length compatible with human circadian biology. Radiation levels reducible to acceptable doses with manageable shielding. Atmospheric resources usable for life support. Surface materials not immediately destructive to equipment and health. Temperature ranges manageable with insulation and active thermal control. By these specific criteria, Mars scores better than the Moon on most axes, despite being much farther and much harder to reach. The Moon fails on gravity, on day length, on radiation, and on dust, in ways that Mars does not fail as severely. This suggests a general principle. Distance and accessibility are not the same as habitability. A world can be easy to reach and hard to live on. A world can be hard to reach and relatively easier to live on. The Moon and Mars are a concrete example of this principle. For the eventual human expansion beyond the solar system, if it comes, this principle will be relevant. The nearest worlds may not be the most hospitable. The most hospitable worlds may require the longest journeys. The selection of destinations for human habitation cannot be based on proximity alone. The Moon teaches this lesson in the most accessible possible place, 3 days from Earth, close enough to observe in detail from the ground, already visited by humans. The lesson is learned at manageable cost. The lesson is then available for application wherever humanity eventually goes next. Let us now talk about one more dimension of the comparison that deserves specific attention, about the psychological and existential difference between the Moon and Mars as human destinations. The Moon is visible from Earth with the naked eye. On any clear night, it hangs in the sky, sometimes a sliver, sometimes a full disk, close enough to resolve features with binoculars, close enough that people have named its prominent craters and seas for centuries. The Moon is familiar in the way that no other world is familiar. It has been part of human culture, mythology, calendar systems, and romantic imagination for as long as humans have been capable of imagination. This familiarity has a specific effect on the psychological experience of living there. Lunar residents would be able to see Earth with the naked eye, and would see it as the dominant feature of the lunar sky, large and blue and unmistakably alive against the black backdrop. This perpetual view of home, a view unavailable from any more distant destination, has a specific character. It keeps Earth constantly present. The 1.28-second communication delay maintains a real-time connection. Earth is not a memory or a photograph. It is there, visible, responsive. For some lunar residents, this might be comforting, a connection to home maintained by direct sightlines and real-time communication. For others, it might be a source of longing, a constant reminder of everything left behind, visible but unreachable. Mars residents would not see Earth as a disk. Earth from Mars appears as a bright point of light, recognizable as a planet, occasionally the brightest object in the Martian sky after the Sun and possibly the Moon, but not a visible presence the way it is from the Moon. Communication with Earth takes 3 to 22 minutes each way, not real-time conversation but asynchronous exchange. Earth is present but not immediate. This difference between Earth as a constant visible presence and Earth as a distant point of light changes the psychological character of the isolation profoundly. Lunar isolation is isolation in the presence of home. Martian isolation is isolation at a distance, where home is no longer immediately present. Whether one is more bearable than the other depends on individual psychology, but they are genuinely different experiences. And the design of habitats, social structures, communication protocols, and mental health support systems would need to reflect this difference. There is also an existential dimension to consider. Going to Mars means going far enough that return is neither quick nor guaranteed. A Mars resident commits to months of transit each way and years of separation. This is qualitatively different from a lunar resident who knows that in an emergency, a true emergency, a rescue is theoretically possible within a week. This commitment, this deeper cut from the umbilical of easy return, may attract a different kind of person than lunar habitation. Not necessarily a more courageous person, but a person with a different relationship to the concept of home, a different tolerance for irreversible decisions, a different psychological makeup in the face of genuine rather than theoretical isolation. Understanding what kind of person thrives in each environment, what psychological profiles are most resilient in the specific conditions of lunar and Martian habitation, is itself a research program that has barely begun. The Mars 500 study, which confined volunteers in a simulated Mars mission environment for 520 days, provided some data. Antarctic winter-over studies provide some data. But neither analog is perfect, and the genuine article, Actual Human Presence at These Destinations, will provide data that no analog can fully substitute for. The Moon will provide the first genuine data. The lessons learned from the first permanent lunar residents about what they struggle with, what they adapt to, what supports their resilience and what undermines it, will shape everything that comes after. That is the ultimate importance of the comparison between living on the Moon and living on Mars. Not merely to determine which is safer in the abstract, but to understand, through the experience of actually being there, what humans are capable of in environments that our species has never before inhabited. The Moon is first. It is not the easiest destination, but it is the most accessible. And the knowledge gained there about radiation, about dust, about gravity, about psychology, about medicine, about engineering, is the knowledge that makes everything else possible. Let us talk about something that requires a specific kind of attention, about the water ice at the lunar South Pole, and why it is simultaneously one of the most valuable resources in the solar system and one of the most difficult to access safely. The presence of water ice in permanently shadowed craters near the lunar South Pole has been confirmed by multiple lines of evidence. The LCROSS mission in 2009 deliberately impacted the Cabeus crater and spectroscopically detected water in the ejected plume. The LRO spacecraft has mapped hydrogen concentrations consistent with water ice in polar regions. The Chandrayaan-1 mission detected water signatures using infrared spectroscopy. The presence of water ice is not in question. What is in question, and what remains one of the most significant unknowns for lunar settlement planning, is the form, concentration, and accessibility of that water. The water ice is almost certainly not a solid sheet of pure ice like a frozen lake. More likely, it exists as ice mixed into the regolith at various concentrations, perhaps as isolated ice grains distributed through the soil, perhaps as layers of higher concentration ice at specific depths, perhaps as frost on the surfaces of soil particles. The specific distribution matters enormously for how it can be extracted. The permanently shadowed craters containing the ice are at temperatures near -200 degrees Celsius, cold enough to preserve water ice for billions of years, but also cold enough to make any engineering operations extraordinarily challenging. Equipment designed for lunar surface operations at equatorial or mid-latitude temperatures may not function at all in permanently shadowed crater interiors. Lubricants freeze, electronic components lose efficiency or fail, battery performance degrades severely. Operating mining equipment in permanent shadow, in extreme cold, in an environment where any malfunction cannot be quickly repaired by a person in a spacesuit, because a spacesuit designed for the relatively warmer, illuminated lunar surface may not protect against -200-degree temperatures, is a genuinely hard engineering problem. There is also the radiation environment inside permanently shadowed craters. Without direct solar illumination, these craters have no solar wind bombardment of their interior surfaces, but galactic cosmic rays penetrate everywhere, and the secondary radiation produced by cosmic rays interacting with the ice-bearing regolith may create a locally elevated radiation environment inside the craters, a factor that has not been fully characterized. The geometry of the South Polar region also creates operational challenges. The best settlement sites, the illuminated ridges and crater rims receiving near-continuous sunlight, are adjacent to the permanently shadowed craters, but not inside them. Getting from the illuminated settlement area to the interior of the shadowed craters requires traversing crater walls at angles that may be challenging for rovers and equipment. The terrain at the South Polar region, based on orbiting spacecraft imagery, is extremely rugged, far more difficult than the relatively flat Mare regions where Apollo landed. This means that extracting South Polar water ice requires a supply chain, a system that operates mining equipment in the cold dark of crater interiors, transports extracted ice or processed water up crater walls to processing facilities in the illuminated zones, and delivers the product to the settlement. Each step of this supply chain presents engineering challenges that have not yet been solved at any scale. The water is there, the need for the water is real. The path from one to the other is not yet clear. Let us now talk about something that provides a useful context for all of these challenges, about the history of human exploration in extremely hostile environments on Earth, and what it teaches about the psychology and engineering of survival at the frontier. The most direct analogue on Earth for lunar or Martian habitation is Antarctic winter over stations. Research stations like McMurdo, Concordia, and the Amundsen-Scott South Pole Station maintain small crews of 10 to 50 people through the Antarctic winter, a period of complete darkness, temperatures reaching -80 degrees Celsius, and complete isolation. No aircraft can land or take off during the winter months. If someone needs emergency medical care that cannot be provided at the station, they must survive until the sun returns months later. This is not the same as lunar or Martian habitation. Antarctica is on Earth. The atmosphere is breathable, gravity is 1g, cosmic radiation is shielded by the magnetosphere and atmosphere, the surface cannot contaminate lungs with reactive dust. But the psychological and social dynamics of small, isolated crews in extreme environments, separated from civilization for months with no option for emergency evacuation, provide genuine data on human resilience and human breakdown. Antarctic winter-over research consistently identifies several patterns. Interpersonal conflict is the most significant source of psychological stress, not the environment itself, but the difficulty of sharing confined space with a small number of people you cannot escape. The third quarter phenomenon, the period after the midpoint of winter but before the end is near, is reliably the most psychologically difficult period. Sleep disruption is universal in the constant darkness of winter. Cognitive performance declines measurably. Solutions developed for Antarctic environments are directly applicable to lunar and Martian habitations. Crew selection processes that identify psychological resilience and interpersonal compatibility. Structured social environments with clear roles and responsibilities. Communication protocols that maintain connection to family and support networks on Earth. Physical exercise maintained as a routine rather than optional. Mental health monitoring by peers trained to recognize deterioration. But Antarctic analogues also show the limitations of analogy. The people who winter over in Antarctica know they will return to normal life in months. They know that in a genuine medical emergency, a helicopter might be possible to arrange at great expense and risk. They know that the Antarctic environment, hostile as it is the surface of Earth, with breathable air and familiar gravity. The specific stresses of lunar habitation, the awareness of the radiation environment, the knowledge that the dust on your suit might be slowly damaging your lungs, the absence of the familiar day-night cycle, the view of Earth hanging perpetually in the sky, are not replicable in Antarctica. The International Space Station provides another analogue, a small crew in an isolated, enclosed environment separated from Earth. The ISS research program on long-duration spaceflight psychology has produced valuable data on cognitive performance, interpersonal dynamics, sleep, and the specific stresses of microgravity spaceflight. But ISS is in Earth orbit, with real-time communication possible and emergency return achievable within hours in a Soyuz capsule. The depth of the isolation is not comparable to what lunar permanent residents would experience. There is no perfect analogue for living on the Moon. The closest thing to a perfect analogue is living on the Moon. This is why the Artemis program, whatever its specific political and programmatic history, represents something genuinely important. The data gathered by the first humans to spend weeks and then months on the lunar surface will be qualitatively different from any analog data gathered on Earth or in low Earth orbit. It will be the first actual data on human life in an environment that combines all of the specific parameters of lunar habitation simultaneously: the radiation, the dust, the gravity, the day-night cycle, the specific psychological character of the view from the Moon. That data will shape everything that comes after. Let us now talk about something that is rarely foregrounded in discussions of lunar versus Martian habitation, but that may be one of the most important long-term considerations, about what a permanent human presence at either destination would mean for the long-term trajectory of the species. The core argument for human expansion beyond Earth is ultimately about risk reduction. A species confined to a single planet faces existential risk from any of a range of catastrophic events: asteroid impact, pandemic, nuclear war, supervolcanic eruption, long-term climate change, or any of the other mechanisms by which a planetary civilization could be destroyed or permanently disabled. A species spread across multiple worlds is more resilient. The extinction of any one population does not mean the extinction of the species. This argument is most compelling when the off-Earth populations are truly independent, capable of surviving without support from Earth, with sufficient genetic diversity and population size to maintain a viable civilization indefinitely. Neither a small lunar outpost nor a small Martian settlement achieves this independence in the near term. A crew of 6 to 12 people cannot form a genetically diverse, self-sustaining civilization. They are an outpost, dependent on supply and rotation from Earth, contributing to the long-term goal, but not yet achieving it. The question of what population size and what level of self-sufficiency is required for genuine independence, for a settlement that could survive indefinitely, even if Earth were suddenly made uninhabitable, is a specific quantitative question with a range of answers depending on assumptions about technology, resource availability, and what level of diversity is required for long-term genetic and cultural viability. Most estimates suggest that a genuinely self-sustaining off-Earth civilization would require at minimum thousands of people, preferably tens of thousands, with the technological capability to reproduce all the critical technologies the civilization depends on. Getting from a crew of 12 to a population of thousands requires a sustained commitment of investment and political will over generations. Whether the Moon or Mars is the better site for this eventual self-sustaining civilization depends in part on the factors we have been discussing all night. The more favorable physical environment of Mars, in radiation, in gravity, in day length, may make Mars a more plausible long-term home for large numbers of people. But the accessibility of the Moon, the ease of supply, the ability to rotate crews, the option of emergency return, makes the Moon the more practical site for the early phases of development. The Moon and Mars may both eventually host permanent human populations. The Moon's population would be smaller, more dependent on Earth, more technically challenging to sustain in the hostile physical environment, but more connected to Earth through proximity and communication. The Martian population would be larger, more self-sufficient, physically somewhat more comfortable despite the distance, and more genuinely independent. This two-destination vision, Moon as outpost and laboratory, Mars as home, is the structure underlying most serious thinking about the long-term human future in space. The dangers of the Moon, understood correctly, are not reasons to abandon lunar settlement. They are specifications, engineering requirements, and medical research priorities that define what must be built and what must be understood to make lunar settlement work. Each danger identifies a problem. Each problem points toward a solution. The solutions developed for the Moon become the toolkit for Mars. Let us now talk about something concrete and near-term, about the specific technologies that do not yet exist but that are most critical for making permanent lunar habitation viable. Nuclear power is the most fundamental. The lunar night problem, 2 weeks without sunlight, makes solar power alone inadequate for any serious settlement. Small fission reactors capable of providing 10 to 40 kilowatts of reliable power through the lunar night are essential. NASA's Killer Power project demonstrated a working small fission reactor design. Development to flight-ready hardware has not yet been completed. This is the single most important technology gap for lunar settlement. In situ resource utilization at scale. MOXIE demonstrated oxygen production from CO2 on Mars. The lunar equivalent, producing oxygen from regolith oxides, extracting and processing water ice, has been demonstrated at laboratory scale, but not at operational scale. A lunar settlement of any size needs to produce significant quantities of water, oxygen, and potentially propellant from local resources. Scaling up from laboratory demonstrations to field-deployable, reliable production systems is a major engineering challenge. Dust mitigation at the engineering level. The electrostatic dust shield concept needs to be validated in actual lunar surface conditions, not laboratory simulations. Spacesuit materials and designs that resist dust adhesion need to be tested at the surface. Airlock designs that prevent dust infiltration into habitats need to be proven. None of this has been done in actual lunar conditions. Radiation-hardened electronics and materials. Equipment intended for long-duration lunar surface operations must be designed to function in the lunar radiation environment over years. The cumulative radiation dose to electronic components over years of lunar surface exposure exceeds the tolerance of many commercial components. Radiation-hardened alternatives are more expensive and often higher in mass, but are essential for reliable, long-duration operations. Closed-loop life support. ISS uses partially closed life support. Water is recycled at high efficiency, but oxygen and food are supplied from Earth. A permanent lunar settlement needs fully closed or near fully closed life support, recycling essentially all water, producing oxygen from regolith or CO2, growing food locally. The technology exists at small scale, but has not been operated at the reliability and scale needed for permanent settlement. Telemedicine and autonomous medical capability. A permanent lunar settlement needs medical capability to handle any medical emergency without evacuation. Not because evacuation is impossible from the Moon, but because the faster a settlement can function autonomously, the more viable it is. Medical robotics, diagnostic AI, pharmaceutical manufacturing, surgical capability by non-surgeons guided by AI. These technologies are developing rapidly on Earth and will be critical for any off-Earth settlement. Advanced construction techniques for regolith. Using lunar regolith as a construction material, for radiation shielding, for structural elements, potentially for pressurized structures, requires techniques for melting, sintering, or otherwise processing regolith into useful forms. 3D printing with regolith has been demonstrated at small scale in laboratory conditions. Operational scale construction from regolith in the actual lunar environment with the specific properties of lunar regolith has not been demonstrated. Each of these technology gaps is significant but not insurmountable. They are engineering problems with engineering solutions. They require investment, time, and focused development programs. The question is not whether they can be solved, but whether the will and resources exist to solve them before people are placed in environments that depend on those solutions. That question, the question of sustained political and financial commitment, is ultimately the most uncertain variable in any timeline for permanent human presence on the Moon. The physics and engineering are challenging but tractable. The human institutions that would fund and sustain the effort over the necessary decades are less predictable. The specific dangers of the Moon, the radiation, the dust, the gravity, the temperature extremes, the night length, are fixed physical facts about a specific world. They do not change. They define what must be built and what must be understood. They are specifications for the civilization that would inhabit that world. Meeting those specifications is what the work of lunar habitation actually is. Let us talk about something that connects all of the technical challenges we have discussed to a single unifying question, about what it actually means to design a life support system that must never fail. On Earth, life support is provided by the planet itself. The atmosphere maintains pressure and oxygen concentration. The magnetosphere and atmosphere filter radiation. Gravity maintains the physiological systems evolved to function in it. The hydrological cycle provides water. The biosphere provides food. These systems have operated continuously for billions of years, with a reliability no human engineering project has ever approached. When humans leave Earth, they must substitute artificial systems for each of these natural functions. And the substitution must work without interruption, because interruption means death. This is a fundamentally different engineering challenge from building systems that work most of the time. A computer that crashes occasionally is annoying. A life support system that fails occasionally kills people. The reliability requirements for life support are more stringent than almost any other engineering domain, comparable to the most critical systems in commercial aviation, where a failure rate of 1 catastrophic event per billion flight hours is the target. Achieving this reliability is hard. The Apollo program flew 17 missions and had one near-catastrophic failure, Apollo 13. The Space Shuttle program flew 135 missions and had 2 catastrophic failures, Challenger and Columbia. The ISS has operated continuously since 2000 and has had multiple life support system failures, all manageable because of redundancy and the ability to evacuate if necessary. For permanent lunar habitation, the calculation changes. A small outpost cannot simply evacuate when a system fails. The systems must be repairable locally, replaceable from local stock, and designed with enough redundancy that single failures do not cascade into life-threatening emergencies. This drives a specific design philosophy: multiple redundant systems for every critical function, with failure modes that are independent rather than common cause, with repair capabilities that can be executed by non-specialist crew members following detailed procedures, with spare parts inventories adequate for the expected failure rates of all critical components over the planned operational lifetime. The reliability engineering required for permanent lunar habitation has not been fully developed. It requires understanding failure modes of specific components in the lunar environment: the radiation, the thermal cycling, the dust, which requires operational experience that does not yet exist. The ISS has provided some of this knowledge for systems operating in low Earth orbit, but the lunar environment is harsher than LEO in significant ways. More radiation, more thermal cycling, more dust, and no option for rapid resupply when something fails. The ISS experience is the best available starting point, but it is not the same thing. Let us now talk about something more immediate, about what the first long-duration lunar residents would actually experience in the first weeks of their arrival, and how the challenges we have discussed would manifest in real human terms. Imagine arriving at the lunar South Pole for a 6-month stay. You have trained for years, you know the technical requirements, you are prepared as thoroughly as preparation allows. The first thing you notice stepping onto the lunar surface is the silence. Not the interior silence of the habitat, the deep, complete silence of a world with no atmosphere. On Earth, even in the quietest places, there is sound: wind, biological activity, your own body. On the Moon, outside your suit, there is nothing. The only sounds are the ones your suit makes and the sounds of your own breathing. The second thing you notice is the sky. Not the grey moonscape that dominates photographs, though that is there too, but the sky. Black, completely black, even in full daylight, because there is no atmosphere to scatter light. Stars visible in daylight. Earth hanging overhead, large and blue and alive in the black sky, so bright in the lunar night that it casts shadows. The third thing you notice is the dust. Within the first EVA, your suit has accumulated a grey coating that resists every attempt to brush it away. You bring the suit back inside through the airlock system designed to limit dust infiltration, but some dust gets through. The interior of the airlock smells of something sharp and acrid, like spent matches. You run through the dust removal protocols carefully. The physical experience of moving in 1/6 gravity is initially exhilarating, and then deeply strange. Jumps that feel natural carry you far higher than expected. Movements that feel normal result in trajectories your body does not predict correctly. Your vestibular system, calibrated for Earth's 1G, sends signals that do not match what your muscles experience. Coordination requires conscious adjustment. Within the first week, the novelty has worn off enough that the routine becomes visible. Exercise. 2 hours of vigorous resistance and cardiovascular exercise daily because the alternative is bone and muscle loss that compromises your ability to function. Monitoring. Daily health checks, radiation dosimetry, regular blood draws for bone marker analysis to detect early loss. System monitoring. The constant background task of watching life support systems, checking readings, confirming that the systems keeping you alive are functioning within parameters. The 2-week lunar night begins. Outside, temperatures drop toward -170 degrees. Solar panels shut down or reduce output dramatically. Nuclear power takes over. The habitat maintains its environment, temperature, pressure, oxygen, humidity, without visible change. But you know that outside, the environment is as hostile as anywhere in the solar system. The communication link to Earth remains real-time. Video calls with family are possible. Earth news arrives as it happens. But you cannot go home. The psychological reality of that fact, that you are here in this specific place for months, and that the Earth visible in your skylight window is not accessible to you, settles in over the first weeks in a way that training cannot fully prepare you for. What do the first long-duration lunar residents think about? What matters to them in ways that matter more than the technical details of their mission? The research, the genuine scientific work of understanding the Moon, its geology, its resources, its history, would give the mission purpose and meaning that pure endurance could not provide. Scientists are motivated by discovery. The first humans to survey the South Polar region in person, to examine the ice-bearing regolith directly, to map the interior of a lava tube entrance, to measure the radiation environment with instruments their own bodies carry, they would be doing something genuinely new. The scientific value of their presence would be real and would provide a source of meaning that makes the hardship bearable. The connection to the larger story. The first long-duration lunar residents would know, with a clarity difficult to achieve in ordinary life, that they are part of something that extends beyond themselves. The history of their mission will be written. What they endure and what they learn will shape the missions that follow. The humans who eventually live on Mars will do so partly because of what these first lunar residents experience and survive. That knowledge, that you are the link between the earthbound history of humanity and whatever comes next, provides a specific kind of psychological sustenance. The small things. In extreme environments, the texture of daily life matters more than in comfortable ones. A good meal, in conditions where food is functional rather than pleasurable, becomes disproportionately significant. A private space for a few hours of quiet in an environment where privacy is limited becomes precious. Humour, the specific dark humour of people in difficult situations, becomes essential social glue. The relationships within the small crew, which can be a source of conflict and strain, are also the primary source of human warmth. These are not surprises. They are what Antarctic researchers report, what ISS astronauts report, what anyone in extended extreme conditions reports. The small things become large things when the large things, safety, survival, completion of mission, are under continuous management. The first permanent lunar residents will discover which of their personal strategies for managing difficulty actually work in the specific conditions of lunar habitation and which do not. That knowledge, subjective, experiential, impossible to gather in any simulation, will be as valuable as any scientific measurement they take. Let us now talk about something that lives at the very end of the trajectory we have been following, about what success in permanent lunar habitation would actually look like and what it would mean. Success is not simply survival. It is not the completion of a predetermined set of experiments and the safe return of the crew. Success in permanent lunar habitation means something more demanding, a community that has figured out how to live in that environment sustainably, where the hazards are managed well enough that the residents are healthy and productive over years rather than merely surviving. where the community has developed the local knowledge and operational capability to continue indefinitely without continuous crisis management. This kind of success is not achieved by any individual mission. It is the result of accumulated experience, lessons learned from early missions, problems identified and solved, procedures refined through use, technologies improved based on operational feedback. It is the product of time and iteration, which is why early missions matter so much, even when they seem small and limited relative to the ultimate goal. The history of human habitation of extreme environments on Earth shows that the first parties to spend extended time somewhere rarely establish permanent communities. They explore, they struggle, they learn what is needed, and they report back. The permanent communities come later, built on the knowledge accumulated from the explorer's experience. The first long-duration lunar missions will be the exploration phase. The permanent community comes after, when the problems are understood well enough to engineer against them, when the life support systems have been proven reliable through operational experience, when the medical protocols have been validated and refined, when the crew selection and psychological support systems have been demonstrated to work. That path from first visit to permanent community has been travelled on Earth, in Antarctica, in undersea habitats, in remote research stations. The specific challenges of the lunar path are different in their physics, but similar in their human character. Understanding what is needed is the first step. Building what is needed is the work. And the work has begun. The moon is there. We have been there. We know what it is. The physics of its environment, the radiation, the dust, the gravity, the day-night cycle, are measured facts about a real world that exists 384,400 kilometers from where we are right now. Living there is harder than living on Mars in the specific ways we have examined tonight. Understanding why is the beginning of understanding what must be built to make it possible. The rest is engineering, and the engineering is what comes next. Go outside tonight and look at the moon. If it is visible, and depending on where you are in the lunar cycle, it may be a sliver or a half disk or a full bright circle. Find it in the sky and look at it for a moment before reading further. That object is 384,400 kilometers away. Light takes 1.28 seconds to travel between you and its surface. The Apollo astronauts made the journey in 3 days. It is close, closer than anything else we have visited in space, closer by orders of magnitude than Mars, closer than any serious space exploration destination except the space immediately around Earth itself. And it is, in the specific ways we have examined tonight, more dangerous to live on than Mars. Not more dangerous to reach, not more dangerous to visit briefly, more dangerous to live on, to make a home, to stay for months or years, to build the kind of permanent presence that would make humanity something more than a single planet species. Here is what makes it more dangerous: the radiation. The moon has no magnetic field and no atmosphere. The surface of the moon is exposed directly to the full radiation environment of space. Galactic cosmic rays from distant supernovae, solar particle events that can deliver dangerous doses in hours, the continuous low-level bombardment of the solar wind. An astronaut living on the lunar surface without adequate shielding would receive approximately 380 millisieverts of radiation per year, far above any accepted safe limit, sufficient to significantly elevate cancer risk over months to years. Mars, with its thin atmosphere providing roughly half the shielding of the lunar surface, is measurably less irradiated. The difference is real and clinically significant. The dust. Lunar regolith has never been weathered. No wind, no water, no chemistry has rounded its edges. The particles are microscopically jagged, glassy, extraordinarily reactive. Freshly fractured silicate surfaces that have never been passivated. They cling electrostatically to everything. They penetrate into equipment, into seals, into the moving parts of machinery. Inhaled, they are more damaging to lung tissue than almost any terrestrial dust. Similar in character to the industrial dust that causes silicosis, but potentially more reactive and more harmful. For brief Apollo visits, this was manageable. For permanent residents, it is a chronic health threat, requiring ongoing engineering mitigation that has no complete solution. The day-night cycle. Any location on the Moon that is not at the poles experiences 2 weeks of continuous daylight, followed by 2 weeks of complete darkness. During the day, surface temperatures at the equator reach 127 degrees Celsius. During the night, they drop to minus 173 degrees. A 300-degree temperature swing over each 29.5-day cycle. Solar power, the most practical energy source, is completely unavailable for 2 weeks at a time. Thermal cycling of that magnitude stresses materials, fatigues seals, and requires active thermal management through systems that must function reliably through the entire cycle. Mars, rotating in 24 hours and 37 minutes, has a day-night cycle that closely mirrors Earth's. Solar power works normally. Temperature swings are severe, but not on the same scale. Equipment is not subject to the same thermal fatigue. The gravity. The Moon's surface gravity is 0.165 g, 1/6 of Earth's. Whether this is sufficient to maintain human bone density, muscle mass, cardiovascular function, and fluid distribution over years is unknown. The human body evolved for 1 g. In zero gravity, which is worse, bone density decreases at 1 to 2% per month, and muscle mass decreases rapidly without vigorous countermeasures. Lunar gravity provides more mechanical loading than 0 g, but only 1/6 of what the body was built for. Mars at 0.375 g provides more than twice the loading of the Moon, still below Earth, still requiring study, but more plausibly compatible with long-term health. The circadian mismatch. The human body runs on a 24-hour internal clock synchronized by light and dark. A lunar day is 29.5 Earth days. There is no usable light-dark cycle on the Moon for circadian synchronization. Residents in shielded habitats must create artificial day-night cycles, which is technically possible, but adds another engineered system that must work reliably and removes residents from any natural environmental rhythm. Mars, with its 24-hour 37-minute sol, provides a day length close enough to the human circadian period that biological adaptation is plausible. On each of these axes, radiation, dust, temperature cycle, gravity, circadian compatibility, Mars provides a less hostile environment for permanent human habitation than the Moon. And yet, the Moon is 3 days away. Mars is 6 to 9 months away. The Moon allows real-time communication, 1.28 seconds each way. Mars imposes communication delays of 3 to 22 minutes each way, making real conversation impossible and emergency response from Earth essentially meaningless. A medical crisis on the Moon can in principle be addressed through emergency evacuation within a week. A medical crisis on Mars must be resolved by whoever is there with whatever is available, with no help coming. The Moon is harder to live on. Mars is harder to reach and harder to rescue from. This combination, this specific pairing of difficulties, defines the challenge of human expansion beyond Earth in its most concrete form. The Moon teaches what must be learned before Mars is attempted. Its radiation environment defines the shielding requirements that any serious off-Earth settlement must meet. Its dust defines the material compatibility challenges that must be engineered around. Its gravity defines the physiological research that must be conducted before humans commit to decades in sub-Earth gravity. Its extreme temperature cycles define the energy systems and thermal management approaches that must be proven reliable. Its challenges, in aggregate, are a curriculum, a specific set of problems whose solutions are prerequisites for everything that follows. Mars is the destination. The Moon is the school. Every research program needed for Mars settlement can be conducted more safely and more cheaply on the Moon because of the Moon's proximity. If a life support system fails on the Moon, rescue is possible. If a medical situation exceeds local capability, evacuation can be attempted. If an engineering approach proves inadequate, the crew can return and the approach can be redesigned. None of this is available on Mars. And the Moon has its own scientific value that is independent of Mars. Its ancient, unweathered surface is a geological archive of the first billion years of the solar system's history. Its permanently shadowed craters preserve water ice that has been accumulating for billions of years. Its far side is the quietest radio environment accessible to humanity, shielded from Earth's electromagnetic noise by 3,500 kilometers of rock. These are not consolation prizes, they are genuine scientific assets. The Moon is not a lesser version of Mars. It is a different world with different dangers and different opportunities. Understanding the specific character of those dangers, understanding why the radiation environment is worse, why the dust is more dangerous, why the day-night cycle is more disruptive, why the gravity may be less compatible with long-term health, is not pessimism about lunar settlement. It is the beginning of designing lunar settlement correctly. Look at the Moon tonight. That world, 384,400 kilometers away, visible to the naked eye as a familiar companion in Earth's sky for as long as humans have had eyes to see it, is the most hostile permanent human habitation site in the solar system within reach of current technology. More hostile than Mars in the specific ways that matter most for human biology, more demanding in its radiation, its dust, its temperature extremes, its gravity. And it is also the most accessible, the most studied, the most reachable. The place where the first chapters of the story of humans living beyond Earth will be written. The dangers are real. The knowledge of those dangers is exactly what is needed to build the things that make survival possible. That work is beginning. The Moon is waiting.